In this video we're going to go a little further into PTF. We'll start out looking at a simulated data set, the SDF, and then we'll return and have another look at Wcom. So to begin with, let's open our workbook 104 and go to SDF. This one here, SDF stands for Single Development Factor. And this data set, I'll load the model here, based on the actual parameters, is based on a very simple model in which there's a single development factor minus 0.3, that's a decay along the development direction. The accident levels are flat, the calendar years are flat. So in a case like this, we have something like this for each development period. Let's put the development along this axis and the mean along this axis. So the mean decreases along the development period, but in each cell we have on the log scale, a normal distribution. I'll try to draw that bell-shaped curve there. And then a little further on, we've got a normal distribution with exactly the same variance. So it's as if I just took this distribution curve and shifted it down, and so on all the way down. So along the development, these incrementals are just drawn from these normal distributions on the log scale. On the dollar scale, it turns into log normals. But they're done with a fairly high variance. So the variance figure here from the model is just the mouse there, 0.4076. In fact, when the simulation was created, the value was 0.4. And when we do our forecasting, we'll forecast with the 0.4. So let's begin by taking a look at the data, and I'm going to take a look at it on the cumulative data as well, as if you just received this as a cumulative. So what I did was just right-clicked here, went transform, and created this cumulative version of the same data set. So let me plot this, and this time, if I look at the data plot, it looks like this, like cumulative data. Notice the accident years appear to be, the accident levels appear to be going up and down, even though we know from the underlying true parameters that there is no difference in the accident levels. However, our simulation is of the incrementals, so little changes are going to accumulate. If the first simulated value was quite low, then the rest of that accident year will end up low. And actually we see the same level of variability in each accident year pretty much, but the overall levels change as they get added together. Now we get a nice plot if we actually look at the three-dimensional plot. Now I'll switch that to ribbons. So now you see a ribbon line for each accident year, and I can swing that around with this button here. And you can see how different they are between, say, this one here, that's 1979, I think it is, and this one here, 1980. There's a considerable difference. In fact, again, the development periods are all consistent, but they come out looking fairly different. Let's have a look at the 3D plot of the incrementals, just by contrast. I'll do the same thing. Now when I look at it on the dollar scale, you can see a considerable amount of volatility there. and not a great deal of order. However, if I switch to the log normal, you can actually see, you can almost see the underlying model, which was simply this straight line. That's the positive development direction. I can, yes, that now it looks like my graph. So there we have the, as the development years proceed, the mean decreases. There's a considerable amount of volatility around the mean, but the rate of decrease is constant. So we pick up that structure in this graph, but we also see quite a high degree of volatility there, which is going to make life interesting. Okay, now staying with the cumulative for the time being, let's open this in ELRF. So this gives us our MAC-style volume-weighted average model, and we see the residuals here are fairly flat in development. Put this up and down structure in the extant direction. What's interesting here is that we have a downward trend, fairly consistent downward trend in the residuals versus fitted values, and that means that we're overfitting the large values and underfitting the small values. So we would expect probably to get an overly high result here. We could compensate for this to some extent, perhaps by putting an intercept in our ratios. So let's do that. Let's choose the let's choose the Cape Cod method. Let's start with both. So this is intercept and ratio. And if we do that, we do get much flatter residuals here. If we look at the regression table, we see that many of these constants, the ratios are quite close to 1 and considered statistically insignificant. So if we optimize, we end up with this, which is pretty much the Cape Cod model. You've got ratio of 1 but intercepts in each period. And there's a skewness here in the residuals, which comes from, there it is there. On the dollar scale, we're working on the dollar scale here, but there's a high variability in our original log normals, so the log normals are all quite skewed, and we're picking that up in the residuals on the ratio method, so you can see that they're more bunched up closer to the line on the negative side than on the positive side. So we could try various other things there, but that we can also look at the ratios, the degree to which the cumulative is correlated with the following incremental. So this is the predictive power of the cumulatives, the ability to predict the next incremental. Now we actually know from the way this model is set up that the cumulatives have very little power to predict the next incremental. The cumulatives predict the next cumulative quite well, but they can't really predict the innovations, and in fact we get very low correlations here. Okay, so that's just a little bit about using the diagnostics in ELRF. We might return to that later. Let's go back to the PTF and load our actual model. Now what I want to do here is a forecast in which I'm going to add one more accident year, and I'm going to combine the forecast tables. And I'm doing that because I want to see what a year looks like where every cell is forecast using our model. And in future parameters, I'm going to change the future variance to 0.4, which was in fact the number that was used in the model. So I run this and I can see that I have fairly high level of fairly high CV in each of these cells, my aggregate. And well, it's a little over 10%. Oh, I can find the actual number here. Notice that these CVs of the accident years are decreasing as you go down the table, fairly consistently decreasing, and that's because we're predicting more cells in the later years, and when you add those cells together, even though there's some positive correlation between them, and even though they each have a high CV, when you add them together, the CV is lowered. The more cells you've got, the more the averaging effect kicks in. Between accident years, there's no particular relation, so when we add the accident years together, we get a large diversification benefit, as it were, and that's why we end up with 11% CV in our aggregate there. Now let's go back to the forecast table and let's get the combined table. Now the last line of the combined table is our future year 1995. This has no past data at all. So the number here, 103168, corresponds to, based on the raw model itself, what the ultimate should be. This is actually all the accident years are the same. This is the shared ultimate for every one of those accident years. So we're going to do something with that in a minute. But let's just look at these numbers a little more. And I want you to notice the way that the observed here, the blue numbers, often differ quite considerably from the black numbers, which are the means. Look at this cell here. The observed is 68,000. The model figure is 14,000. Where the observed is larger than the model figure, it often tends to be quite a lot larger. But most of the time, the observed is a little lower, or quite a bit lower. So this is the skewness of the distribution operating here. Someone might look at this and think, well, the model fit's not that great because here we have these quite large differences between the model figure and the observed figure. But in fact, these figures are entirely appropriate because they're taking into account the high volatility, the process volatility intrinsic to the data itself. So let's go back to this 103168. So this is the actual ultimate, the mean ultimate for every one of these years. So what I want to do is create a premium vector which will have this number in as the premium for each of the accident years, and then look at our forecast again and see how it goes in terms of loss ratios. So let's go back to the triangle group here. I'll write down this number before I forget. 103168. Now back to the triangle group. Click here on exposures, inflations, premiums, and I'm going to create a new premium vector. I can do this either by clicking on the new premiums button or by right-clicking and choosing a new premium. And I'm going to put this number 103168 in there, and then propagate that down with the F4 key. I'll save this, and then I'll associate this premium with this data set. So now, if I go back, I may need to. I think I can just stay with the same model. Simply rerun the forecast. So the same forecast, rerun it, and this time when I open the forecast summaries, I have a tab here for loss ratios, and this has the premiums that I just entered for each year, and then it has the paid to 1994, which is the final year of our forecast period. So each of these numbers here is actually a conditional mean of the ultimate. It's saying in a certain year, I can see that I've paid, like 1982, up till the last year, 1992. Well, I have 3 years of data, and I see that it looks as though I paid 1992. I paid somewhat more than the model would have predicted. So in 1992, my forecast for the ultimate, sorry, this column's the forecast for the ultimate, is 118. So it's a little over the 103, because I can already see that in those initial 3 years, or somewhat over the mean. And so what it does, it takes into account what you've paid up to this point, how that sits in relation to where you would have been had you simply paid the mean each time. And if you're below that, then your ultimate will end up below the 103. If you're above that, your ultimate will end up above the 103. So then we get this collection of loss ratios, which vary quite considerably. But overall, for the entire aggregate, the loss ratio is fairly close to 100. In this case, it's a little over 100. Of course, we made the premium exactly equal to the mean, so that did give us a 50-50 chance of coming in the aggregate above the mean, or in our total losses. So to ensure profits, you would, of course, have to set your premium to be somewhat above the mean expected loss, mean expected ultimate for each accident year. So this table here is the reserve forecast summary. It only goes up to 1994. Our future accident year was 1995, so I could also, and I will in a second, pull up the combined forecast summary. The difference I would expect to find is that the total in the combined will have one more year, the 1995 year, of 103,168, since we haven't paid anything in 1995 yet. So the total mean outstanding will be 284,125 plus 103,168, so about 387, which is there. The CV is the same in this case, even though the year 1995, our estimate there has a CV of 27%, but when you add it in with the other years, we get 11%. Okay, let's go back to the reserve. Let's see how this compares to the ELRF. I'll go back to the ELRF, and let's back to the just the standard MAC type ratio model. So here we can see that there's this overfitting on the large values, so we would probably expect the forecast to be somewhat on the high side. And what do we find? Well, it's on the low side. However, it has a large, quite a large standard deviation, which probably, well, it's lower than it ought to be by about 30,000. The standard deviation is about 30,000 higher than the other, so that makes up to some extent. In what it loses in accuracy, it gains in fuzziness. So here the smaller values dominate in the forecast region, so since they're mostly later development periods, and so the fact that we underestimate in the smaller numbers there ends up having more effect than the fact that we overestimate in the larger numbers. If we choose the, well, take the Cape Cod method, So here the residuals there are fairly flat. We only have this skewness to deal with. And then run the forecast. Here our 282. Well, that's fairly close with a CV of 12. So we did quite well in this case, and we could have congratulated ourselves had we known that the Cape Cod was the right approach to take. We might just as well have tried a different set of averages here, the arithmetic averages, and then produced yet another quite different result. Okay. Now I want to shut this one down and go back to close all PDF models. Go back to Wcom we were looking at in the previous video, and here I'm going to just redo the wizard model. So we'll use the one with the inflation PLI. So I'll remove these three wizard models and just recreate them. So now we have M6. What I'll do is load M4, which turns out to be exactly the same as M6, and then I'll load M1, which is a little bit different. And let's see what that difference amounts to. If we look at the number of points involved, we see that M1 has 3 fewer points than M4, so it's removed certain points as outliers. And in fact, if I restore M4, I can see exactly where those points are. Enlarge that a bit. So there's 2 there and there's 1 there. These 2 look as if they're fairly centered. This one, there might still be a case for treating this as an outlier. Let's see where it sits here. Oh, there it is there. It's quite far off on the low side. So I think we will remove this point and create a new model. So I've clicked on that and turned it black and then re-estimated. So what's this done now? So now I have 117 points. Now the other differences are that the in fact, by removing that point, my normality score has gone up to greater than 0.5 in this modified M4, which was the same normality score as we found in M1, but M1 achieved that by removing 2 more points than I've currently removed. The BIC, which is a measure of model appropriateness, model fit, it's minus 64. The lower this is, the better. In M1, it's minus 64, but M1 has fewer points. M4, it was minus 53, not quite as good. But when I take the modified M4 with 1 more point removed, I get a BIC of minus 62.8, which I think is pretty much of the same level as the minus 64.4. So I think we'll be happy to stick with this model here, which I will now name. Well, I'll call it good 1, which is in fact already exists. So in this model, I now have a final calendar trend of 0.5. Now another investigation I might want to do here is looking at the residual plots. In particular, in the accident years, I noticed that there is a drop here in the last few accident years. It hasn't been picked up by parameter. If I right-click here and reinstate the alpha parameters and then try to put a parameter here where the drop occurs, estimate. Let me just visualize regression tables. I don't need this, and I don't need this. I can see the new parameter that I put in is treated as insignificant. So if I optimize it, it disappears and basically back to where I was before. I still want to keep this one. What if I try putting it here? Well, now it does retain this parameter. So now I have a slightly higher final calendar trend, and this drop is registered here. Now another way I could deal with this drop, let me reinstate the alpha parameters, have this one in here. This time when I optimize, I'm going to go for least significant difference first. And this way, any two alpha parameters that appear to be fairly close, it will measure the statistical significance of their difference. And if they look to be about the same, it will equate them. So here it's created a constraint. It's put the new parameter in, created a constraint, and matched it to the level experienced this many years ago, 1978. So here I get a 16% drop, and I get a higher final calendar year trend. So let's stick with this one, and this one I'll save as good too. So now let me load these two models side by side. So there's good 2, and I'll load good 1. And let's see what difference this makes in terms of the forecast. So just to recapitulate, I think I'll put the two model displays next to each other. So in one of them, the accident level stays steady, and the calendar trend is 5%. In the other one, the accident level drops by 16%, but the calendar trend has increased to 7%. So without worrying about the adding on the extra inflation, the economic inflation, 10% or so, let me just run two forecasts from these and see how this change has affected the forecast. So the two default forecasts, and then get the 2 there, and the 2 forecast summaries side by side, and what we see, 205, 203, 7. We see that in fact they're almost identical. So there are two ways of approaching the analysis here, whether if we look at the 2. In one case, we've tried to pick up this drop in the accident years, thinking there may be something in it. In the other case, in this case we haven't. We've just allowed that drop to occur. And the price of modeling this drop in accident levels was that the calendar trend, final calendar trend, increased somewhat, and so the final forecast ended up pretty much the same. Let's just try a forecast again, and this time I'm going to add 10% to each of the, to account for the economic inflation. So now this one gets about 17.5%, and this one gets about 15%. And now let's compare these. 314 and 312, and they're both 8%. So again, they stay fairly close, neck and neck. They both interpret the future in roughly the same way. So that's just an example of the kinds of analyses and scenario testing one can do in PTF. The wizard models usually should be treated as a starting point, and you should go into the wizard model and just have a look and see what it's done with the outliers, have a look and see if there are any trends that are there that haven't been picked up, or any changes that need to be refined in some way, or possibly parameters that have been placed close to the end of the calendar periods, say, that maybe can't really be justified.